So we're going to start with the day 6 homework review, and I chose a few problems to do. There's probably a number of problems on here that people found difficult. This worksheet is kind of mostly difficult problems, but I chose 3 that I thought people would be the most likely to have trouble with. So the first one is 3a. We want to find the derivative of this function, and there's kind of a hint that you should rewrite this thing using a negative exponent before you take the derivative. So I'm going to go ahead and do that. So 5 over sine of 2x to the third, you can view that or rewrite it as 5 times sine of 2x all raised to the negative third. Notice that the 5 is not being affected by the exponent. It's outside the brackets. The other thing that you might notice here is in class I kind of warned you about this. Sine 2x, I just want to emphasize that the 2x is actually on the inside of the sine function here. So if you like, you can add a set of parentheses to make that extra clear. So sine 2x can be viewed as sine of 2x. That's what that really means. So hopefully you can see that this is going to be a problem that requires 2 applications of the chain rule, because you've got 2x inside of sine inside of the brackets raised to the negative 3, so 2 chain rule applications. So we'll start by thinking about inside and outside. I would say that the outside function is 5 blank to the negative 3. So I start by taking the derivative of the outside function. The derivative of 5 blank to the negative 3 is negative 15 blank to the negative 4. Then I write just the original inside function right here in the blank, so that's the sine of 2x. And then I need to multiply by the derivative of the inside function. But the inside function itself is a composition, so its derivative is a little complicated to think about. So instead of thinking about the derivative right now, I'll just postpone it. I'm just going to write sine of 2x and then put a prime on it to indicate that I still need to compute the derivative of that thing in the next line. Or you can do it all at once, whatever. So y prime would then be, again, in this line, I'm just recopying the first term. I'm not actually changing anything because all I have to do in this second line is compute this derivative here, the sine of 2x prime. All right, so what is the derivative of that function? Well, the outside function is sine blank, so the derivative of sine blank is cosine blank. 2x goes on the inside, but then we need to multiply by the derivative of the inside function, which is 2. If you got this problem wrong, my bet would be that you didn't get this 2 because you didn't see that the inside function itself was a composition and required the chain rule. That's what people typically miss on this problem. So it's basically done. We just need to rewrite it. If you notice, it says rewrite this, or it says simplify your answers, which should have a single numerator and denominator. Well, what can we do? The negative 15 and the 2 can multiply to negative 30, but I'll point out that because of this negative exponent, we're going to have a denominator. The sine of 2x is going to go into the denominator like that, and the exponent, of course, becomes positive. This cosine of 2x remains in the numerator, though, and so I think that that is it. Hopefully I don't make any mistakes when I'm doing this. I find that I tend to make more mistakes when I'm typing equations than I do when I'm writing them for some reason. I don't know why. Yeah, so that would be the answer to me. You could also just put the 30 in front if you wanted. Like, that's also fine, but doesn't make any difference. So let's move on to number 11. So this is a pretty tough problem. Find the derivative. Fine, we'll find the derivative. What I would say is that, so let me just copy this function briefly here. So we've got, okay, hold on. The equation editor is being a little weird here. So what I've got is y is equal to 2 square root of x times sine of square root of x. And Again, they didn't use parentheses on this sine function here, but I'm going to add them just to make it extra clear, sort of where the inside and outside are. So first of all, you should notice that, yeah, there's definitely composition going on here. You've got a root x inside of the sine function, but there's also product happening here because you've got the 2 root x sort of times the sine root x here. And so you're going to need to use both the chain and the product rule. I would use the product rule first. As a matter of fact, you have to definitely, you can view the function as one function times another. Certainly there is composition happening, but notice the entire function itself is not a composition. Just this piece of it right here is a composition. So we're going to use the product rule. Now the thing is, I can already see that when I do the product rule, I'm gonna have to be taking the derivative of this guy right here, and that guy is a composition, so I need to be really careful. So what do? I take the derivative of the first function and leave the second function alone. That's what the product rule says. So what's the derivative of 2 root x? I think it's just x to the negative 1/2. 1/2 comes down, multiplies the 2, and cancels. Subtract 1 from the exponent. And then we leave the second function alone. That's the first term of the product rule. Then we have plus. Now we leave the first factor alone, so we just have the 2 root x left alone, but we have to multiply by the derivative of the second function, the derivative of sine of root x. Trouble is that sine of root x is a composition, so to find its derivative we need to use the chain rule. The outside function is sine blank, so the derivative of sine blank is cosine blank. What goes in here? Just the original inside function, which is square root of x. And then we're not done. Chain rule says we also have to multiply by the derivative of the inside function. Derivative of root x is 1/2 x to the negative 1/2. And so that's the derivative. It just needs to be simplified. If you notice, they want you to put your answer over a common denominator. You're going to have denominators because of these negative exponents here. So let's clean up a little bit. We have y prime equals, just thinking about this term at first, all that's going to happen is this x to the negative 1/2 is going to go into the denominator. So you're going to have a square root of x on the bottom, but that sine of square root of x is going to be left on top. Then looking at this term here, I think that this 2 right here will be canceled by this 1/2, so we can kind of forget about those coefficients. What's left over? Well, we are going to have a square root of x in the denominator because of the x to the negative 1/2 term, so let me put that there. And now what else is there? Well, there's a root x that's actually on top right there. And then we have the cosine of root x as well. And I think that we've accounted for everything, right? We took care of the 2 and the 1/2, we took care of this root x, we took care of the cosine root x, and we took care of the x to the negative 1/2. Okay, so there it is. Now, you might be tempted to cancel the root x on top and the root x on the bottom. You definitely could. The only reason I wouldn't is that they said put it over a common denominator. So they actually want you to keep this common denominator here. It's not mathematically wrong if you don't, but for whatever reason they want you to keep it. So I'll keep it, and I think what they want us to do is combine those two fractions into a single fraction. So we'd have sine of square root of x plus square root of x times cosine of square root of x. And that is my answer. All right, and then last problem that I want to go over is number 12. Number 12 is tough and maybe different from any we've done before. I would point out that there's definitely composition happening, right? You've got 9 plus x cosine x inside of the square root function, but notice that you've also got product happening. You've got a product of x times cosine of x. So you are going to have to use both the chain rule and the product rule, but unlike so many of the other problems we've done, this one actually requires that you apply the chain rule first. And the reason for that is that although there is a product happening, it is only happening in a piece of the function, right? X cosine x is a product, but that's just a piece of the function. The entire function does not have the structure of a product. The entire function has the structure of a composition, one thing stuffed inside of another. So we need to use the chain rule first. So the outside function is root blank, right? Or blank to the 1/2. So we take the derivative of the outside function. That's going to give us 1/2 blank to the negative 1/2. What goes on the inside of the blank? Well, just the original inside function, 9 plus x times cosine x. But then we need to multiply by the derivative of the inside function. Now, the inside function is fairly complicated because it has this product structure, and so it's probably a good idea to postpone the differentiation. Just copy the inside function and put a prime on it, right? And remind yourself to take the derivative in the next line. Because if you try to do it all at once, I think you're likely to make a mistake. So I'm just going to recopy the first portion of the expression, the 1/2 9 plus x cosine x raised to the negative 1/2. And now I'll think about what this derivative actually is. We have two terms. You take the derivative of 9 first. That's just 0, so you can just ignore it. But then the derivative of this thing requires the product rule. The first function is x, and the second function is cosine x. So I'm going to need to use the product rule. The thing is, I'm going to keep a set of brackets here, or you could use parentheses, same thing. I'm going to keep a set of brackets there because I know that the product rule on this guy is going to create two terms, right? And I need it to be true that the entire expression is multiplying the rest of this stuff. So they need to be in brackets to make sure I'm really multiplying, by the entire expression. So what's the derivative of this guy? Well, derivative of x is 1, so I just won't write anything. Or maybe I will, whatever. 1 times the cosine of x left alone, plus leave the x alone, and then take the derivative of cosine, that's negative sine, so x times negative sine. So there's the derivative. It just needs to be cleaned up. A couple of things. We certainly know that there's going to be a fraction because of this negative exponent here. So let's create a fraction bar. What's going on the bottom? Well, because of this 1/2 here, the 2 is going to go on the bottom. But then this expression here being raised to the negative 1/2, that's going to give you a square root of that entire guy in the denominator like that. And then all of this stuff is left in the numerator. So 1 cosine x, that's really just cosine x. And then this term here, x times negative sine, that's really just going to be a negative x sine x. So I think that's the answer there. Oh, well, they want you to evaluate this at 0, right? I mean, that's not hard. Just plug in 0 and you'll get some number. But that's the derivative. That's the hard part. So with that done, let's move on to the day 7 stuff. So this is the new stuff that you should be taking notes on. So this is it day 7? Yeah, day 7. So day 7 is the quotient rule. So the quotient rule, like, what is it about? Basically, it tells you how to find derivatives of functions where you have one function on top and one function down below. So let me just remind you what the quotient rule is not, right? If you have one function f divided by another function g, and you want to know what's the derivative of that entire function, I want to remind you that that is not simply the derivative of f over the derivative of g. That is not what it is. If you remember, that's what Billy thought it was. That's not true. It doesn't work that way. The actual rule is unfortunately a little bit more complicated. The actual derivative of f over g, and this is the quotient rule right here, it's given by f prime g minus fg prime all over g squared. So just let's take a second to just sort of inspect this formula. What is it actually saying? you've got two functions, like the top function and the bottom function. The top function's f, the bottom function's g. So apparently the derivative is derivative of the top, that's f prime, times g left alone. That's the bottom of the function, right? Not the derivative of the bottom, just the bottom left alone. And then minus f, that's just the top function left alone, times the derivative of the bottom function. And all of that is divided by g squared. That's the bottom function squared. Notice the mistake that people tend to make with the quotient rule is they tend to misremember it. They often think that in the formula, the bottom of the fraction is the derivative of g squared, like they think it's g prime squared, but it's not. It's just the original bottom function squared, so watch out for that. One thing I want to point out as well is that this expression in the numerator is like literally exactly the product rule, except it's a minus instead of a plus, right? Because the product rule, remember, says that, I'll just write it here, the product rule, remember, says, you know, if you've got fg all prime, that's f prime g plus fg prime. The numerator of the quotient rule and the product rule expression, they're identical except the quotient rule has a minus instead of a plus. And if you remember that, it's a bit easier to remember the formula. So I think that's worth pointing out. So just really quickly, let's prove this. It does not take a long time. We actually do not have to appeal to limits at all. We can just do it with the product rule and the quotient rule. So what I want is and I'll do this quickly because I don't expect you to copy the proof. So what I want is the derivative of f over g. So the first thing I'm going to do is I'm going to rewrite that as f times g raised to the power of negative 1, right? So f over g is the same thing as f times g to the negative 1. To be clear here, only g is being raised to the negative 1, right? Not f. And then what I have here is actually a product of two functions. F is the first function, and then g to the negative 1 is the second function. Maybe I'll put a dot in between these two guys to emphasize that. And so I can use the product rule on this thing. Product rule says take the derivative of the first function, that's f prime, but leave the second function alone. So that's g to the negative 1 left alone. Plus, then I leave the first function alone, so that's f, and I multiply by the derivative of the second function. So the derivative of g to the negative 1. That's a little complicated, so I'm actually going to postpone the differentiation. Derivative of g to the negative 1. And we'll think about what that actually is in the next line. Okay, so I'm just going to copy the first term because, you know, I don't need to do anything with it, plus f times, and now I'm going to think about what's the derivative of this thing. So this is actually a composition. It's a little hard to see that, but it's actually a composition because g itself is a function and g is being raised to the negative 1. If you like, you can put the g in parentheses and maybe it makes that a bit more clear. You can see that the outside function is blank to the negative 1 and the inside function is g, right? So this is a chain rule. It's a composition problem. So chain rule says I take the derivative of the outside function. Derivative of blank to the negative 1 is negative 1 blank to the negative 2. What goes on the inside? Well, just the original inside function, which is g, but then I'm not done because I have to multiply by the derivative of the inside function, which is g prime. And so this is the derivative, but right now it doesn't look anything like that. Like this formula here. However, if you clean up, it will turn into this formula, unless I screwed up somewhere. So let's see. So f prime times g to the negative 1, that g to the negative 1, that just puts g into the bottom of a fraction. So I have f prime on top, g on the bottom. And then let's see, this whole term here, because of this minus 1, the whole term becomes negative. So let me just write a minus. And then let's see, because of this g to the negative 2, I know I'm going to have a fraction, so let me make a fraction bar. What's in the bottom? I think the only thing in the bottom of the fraction is just the g squared coming from this term here. And then what's left on top? Well, I've got the f and I've got the g prime. So let's put those on top, fg prime. It's starting to look like the form that we want, but it's not quite there. Actually, the only thing you need to do to finish up is to put these two fractions under a common denominator. Like this guy here, to get a common denominator with this one here, you can just multiply top and bottom of this fraction by g, and that'll give you a g squared on the bottom, and then we'll combine the fractions and we'll be done. So multiply top and bottom of this guy by g, I get f prime g over g squared minus, and then I'm not changing the second fraction at all, fg prime over g squared. And then if I combine the two fractions, everything's over g squared, f prime g minus fg prime. Okay, yeah, so that's the formula, right? So that's the proof. That's where it comes from. Really quick, some people like to get very clever and they say, oh, that's a cool trick. Couldn't you like never use the quotient rule, and couldn't you like always rewrite every fraction like this as a product and then just do the product rule and the chain rule? Yeah, you could, and you're not good enough to do it, so don't try. Okay, seriously, just don't do it. Like, if you do that, what you're doing is you're taking a relatively simple problem and you're turning it into one of the hardest derivative problems, which is combination, product, and chain. So just don't do it, okay? Seriously. Every year there are people who are like, "Oh, I'm going to do that," and they just get stuff wrong. So don't do that. Examples. All right, so let's just do a few examples. This is a pretty straightforward one. So find the derivative of y equals blah blah blah, 3x minus 4 over 2x plus 5. Why do you need the quotient rule here? Well, because it's one function divided by another. So to find the derivative, we are going to have to use the quotient rule. Let's recall what the quotient rule says. It says the derivative of f over g is f prime g minus fg prime all over g squared, right? So let's just have that in front of us. I just want it on the same screen. So there it is. So what is f? Well, f is just the top function. That's 3x minus 4. What is g? It's the bottom function, which is 2x plus 5. So that's going to give us, in our case, okay, so f prime, that's the derivative of the top. That's just 3, right? Times g, that's just the bottom function, left alone. So 2x plus 5. So the 3 needs to multiply the 2x plus 5. And I got to put it in parentheses so that the 3 multiplies all of 2x plus 5. And now I'm here. That's the minus sign, so I'm going to copy the minus sign. And then I have what? I have f left alone. So that's just the top function left alone. That's 3x minus 4. I'm going to put that in parentheses. Okay? Times g prime, what is that? That's the derivative of the bottom. And the derivative of the bottom is just 2. So I'll put a 2 there. All over g squared. What's g? That's just the bottom function squared, so it's 2x plus 5 squared. Again, notice it's not the derivative of g squared, it's just g squared. So that's the derivative. It just maybe needs to be simplified. You'll notice that you can like distribute this 3 here, you can distribute this 2 here, and so on. So let's go ahead and do that, and maybe we'll collect some like terms, and I don't know. So we have 2x plus 5 squared on the bottom. By the way, don't multiply this out. There's really no good reason to. You should just leave it. But distributing the 3 to these two terms here gives you 6x plus 15. And then distributing the 2 here obviously is going to give you 6x minus 8. But you got to be really careful with this minus sign here. The thing is, you got to remember that this minus sign needs to apply to like everything in this entire expression. And when you distribute this 2 here, you're going to get two terms. You're going to get 6x and you're going to get minus 8. That minus sign needs to hit both of them. So, I mean, one way of expressing that fact is writing minus quantity 6x minus 8. Like I just distributed the 2 to the inside there, right? So you have minus quantity 6x minus 8, which means that as I say, the minus sign is going to distribute to both terms. So it's actually minus 6x plus 8 all over 2x plus 5 quantity squared. Obviously, I think that you can go directly from this line here to this line here. Like, I think that's fine, but just I really want to emphasize, make sure your minus sign is hitting all the terms in this second expression. So now maybe we can combine some like terms in the numerator. It actually seems like just by sheer accident, the 6x here and the minus 6x here cancel, and then the 15 can be added with the 8 to give you 23. So there it is. So that's the derivative. Yeah, so that's the quotient rule, and that's pretty much what these all look like. Um, right, so what else? So now let's do this guy here. So what is the point of this derivative? It's one function divided by another, right? So you need the quotient rule. Or so it seems. Actually, the point of this problem is to try to get you to notice that just because you have one function divided by another doesn't necessarily mean that you need the quotient rule. Okay, you definitely could use the quotient rule on this. You could. But if you think about it, this function can be rewritten. As a matter of fact, we already did a lot of derivatives just like this one on, in the last unit, right? Like, we already know how to find the derivative of this guy. You just need to split the fraction. So if you split the fraction here, you get x squared over x plus 3x to the fifth over x, which can be simplified to just x plus 3x to the fourth after doing the cancellation. And that's a really easy function to differentiate, right? That's a really easy function to differentiate. The derivative would just be 1 plus 12x to the third, and you're done. If you did the quotient rule on this, it would just be such a huge pain. It would just take you 5 times longer. So the lesson of this problem is just because you see a fraction does not necessarily mean you should be using the quotient rule. You really want to ask yourself, can I rewrite this? You know what I mean? Like, before you use the quotient rule. And there's some problems like that on the worksheet. There, pay attention when you're doing the worksheet, because there's definitely a set of problems where it's like, warning, not every problem requires the quotient rule. And we're telling you to look out for stuff like this, where you can split the fraction or do something else, okay? So be on the lookout for that. And now the last example, and this is the last thing that we'll do today, is to find the derivative of tangent, which seems pretty random. Why are we talking about this? Well, the thing is, the tangent function can actually be rewritten using a trig identity as a fraction, as a quotient. So if you do that, we can rewrite tangent as it is sine of x over cosine of x. And so now that's a quotient, that's a fraction, and we can use the quotient rule on this guy here to find the derivative. This is, by the way, this is actually one of the problems from the homework assignment, but people always need help getting through it. So I figured I'd just do it as an example. But, when you do the problem on the worksheet, try to do it from scratch. You know what I mean? Don't just like copy my work. So, so we have to rewrite tangent as sine over cosine, and then I can find the derivative using the quotient rule. So let me once again type the quotient rule so that we have it in front of us. It's f over g prime is f prime g minus f g prime all over g squared. So there's the quotient rule. So to use this thing, we just have to figure out what's f, what's g. F is the top function, which is sine. G is the bottom function, which is cosine. So our derivative, y prime, is going to be, okay, f prime, that's the derivative of the top. The derivative of the top is cosine x times g, that's the bottom function left alone. The bottom function left alone is also just cosine x. Then we have a minus sign, and now we have the top left alone. And the top in our case is just sine of x times the derivative of the bottom, well, the bottom is cosine of x. The derivative of that guy is negative sine of x, all over g squared. So that's the bottom squared. So that's just, cosine squared x. Or you could write cosine of x in parentheses all squared. Same thing. Okay, and this can be cleaned up a little bit, right? Because, I'm going to keep the cosine squared x on the bottom, but in the numerator, you've got cosine x times cosine of x. That's really just cosine squared x. And then this second term, because of the two minus signs, it actually becomes a plus, and you've got a sine of x times a sine of x, so that's going to give you a sine squared x. Okay, that's kind of cool, but hopefully there are like still some vague memories of last year, and this expression here looks familiar to you, cosine squared plus sine squared. Hopefully you remember that that's actually just 1, right? That's 1. Remember that trig identity? So that's just 1 over cosine squared x, and then maybe you're thinking, wait a minute, 1 over cosine squared x, isn't 1 over cosine just like something? 1 over cosine is actually just secant. Do you remember that? 1 over cosine is just secant. So 1 over cosine squared is actually just secant squared. And so that's the derivative of tangent. The derivative of tangent is actually just secant squared. So, all right, so that is it. Those are the examples. The worksheet, is on Canvas. So remember that all of this stuff is due the first meeting of next week. Also, a bit of a heads up, our unit test is going to be a week from today. As I'm recording this, it's Friday, so Friday of next week is going to be our unit test. We'll have a review day, just like usual. But yeah, so hope you guys have a good weekend, and I will see you all later.